Hi guys, we just looked at mechanical systems. Let's now look at the mathematical models of electromechanical systems. As for mechanical systems, electrical systems can basically most of the time be cut down in their most simple core elements. We're going to have a look at these elements and their mathematical expressions. So let's first look at resistors. They're probably the most common electrical element. In this diagram, you can see that the resistance is labeled R, while the current is labeled I, and the voltage V. So the voltage is in volt, the current in amperes, and the resistance R in ohms. Ohm's law states that the voltage V can be expressed as the current in I multiplied by the resistance R. As for the dampers or the spring, the resistance R is actually a given characteristic of the resistor. It is decided when the resistor is built. So quite simply, the mathematical expression for resistance is Ohm's law. It is voltage is equal to the current passing through that resistor multiplied by the value of that resistance. Let's now look at capacitors. Like resistors, they are a very common piece of circuitry in electrical systems. How do they work? Basically, a capacitor is a very small but very fast battery. They are made of two conducting plates which are separated by an insulating layer of material. When you apply a voltage across them, electrons will accumulate on one side of the capacitor. If you remove that voltage and then connect that capacitor to a load, the capacitor will then discharge its electrons in the opposite direction. So what happens here is that you can store energy in the form of electricity and then release it very, very fast. One of the main parameters of capacitors that is also decided when they are built is its capacitance, expressed in farads, which are amperes multiplied by seconds divided by volts. The mathematical expression for capacitors is I, the current, is equal to the capacitance multiplied by the derivative of the voltage over time. So the speed at which the voltage applied across it is changed. Inductors are essentially a coil of conducting material, usually copper. They are represented, as you can see here, where I is the current, V the voltage, and L the inductor's inductance. The inductance is the main parameter of the inductor. It is expressed L in henries with the symbol H and are equal to volts multiplied by seconds divided by amps. The mathematical expression for inductors is that the voltage across the inductor is equal to its inductance multiplied by the derivative of the current going across it with respect to time. We just had a look at the core components of most electrical circuits. Let's now have a look at the electrical laws that apply to them. First of all, the ideal voltage source. As you can see here, it is represented by a circle with a plus and a minus. The V going across the circle is actually the voltage across the voltage source. So an ideal voltage source can retain a given voltage regardless of the current that is drawn from it. Obviously, this is just an ideal concept. It cannot exist in real life, as in real life, every time you draw a current from a voltage source, the voltage will slightly go down. Let's now look at the ideal current source. As you can see here, it is represented by a circle with an arrow going through it. So an ideal current source produces a current that is independent of the voltage across it. Again, this cannot exist in the real world because any current source in the real world will produce a current that will not be independent of the voltage going across it. The voltage always drives the current, as you can see from the Ohm's law equation, V equals IR. According to Kirchhoff's current law, the sum of all the currents flowing into a junction equals zero. What this means is that at any junction of an electrical circuit, there must be as much current going in than current going out. There cannot be any current that is deleted or created at a junction. Here, in this example, you can see a junction represented by a little black dot. You can see that I1 enters the junction while I2 and I3 leave the junction. Therefore, according to Kirchhoff's current law, I1 must equal I2 plus I3. According to Kirchhoff's voltage law, the sum of all voltages around a closed path in a circuit is zero. This is best shown through the example here. As you can see, V1, V2, V3, and V4 are part of the same closed loop. They form a circle that can continue indefinitely in theory. If you add all of these voltages, then you must find that the sum of them is equal to zero. You can see here that V1 is going in the opposite direction of V2, V3, and V4. It is going counterclockwise while V2, V3, and V4 are going clockwise. This means that V1 is actually of the opposite signs of V2, V3, and V4. Hence, you can write that V1 must equal V2 plus V3 plus V4. Or that V1 minus V2 minus V3 minus V4 equals 0. Let's apply this knowledge to model a parallel RLC circuit, also called an oscillating circuit. This circuit is made of an ideal voltage source placed in series with a resistor R and an inductor L. It also contains a capacitor C placed in parallel with the inductor L but in series with the resistor R and the voltage source. We know from before that the mathematical formula for these electrical elements are the voltage across the resistor is equal to the resistance of that resistor multiplied by the current going through it according to Ohm's law. The current going through the capacitor is equal to the capacitor's capacitance multiplied by the derivative of the voltage across it with respect to time. And finally, the voltage across the inductor is equal to its inductance multiplied by the derivative of the current going across it with respect to time. Similarly, as the inductor L, the capacitor C, are in parallel with the load at the point where V0 is measured, we can write that the voltage across the inductor is equal to the voltage across the capacitor, which is equal to V0. Also, according to Kirchhoff's voltage law, because of the closed-loop circuit which is formed between the ideal voltage source, the resistor R, and the inductor L, we can write that Vi minus VR minus VL is equal to 0. And this is because the voltage across the ideal voltage source is of opposite sign to the voltage across the resistor and the voltage across the inductor, and we know that the sum of the three must equal 0. Now looking at Kirchhoff's current law, and more specifically the junction between the resistor R, the inductance L, and the capacitor C, we can write that the current going across the resistor must equal the current going across the capacitor and the current going across the inductor. So IR minus IL minus IC must all equal 0. So we now know that the current IC is equal to the capacitance multiplied by the derivative of the voltage V0 with respect to time. Hence, we can replace it in the Kirchhoff's current law. So we can write that IR minus IL minus the capacitance multiplied by the derivative of V0 with respect to time is equal to 0. As both sides are equal to 0, we can differentiate both sides and keep the right side equivalent to 0. So that gives that the derivative of IR with respect to time minus the derivative of IL with respect to time minus the capacitance multiplied by the second derivative of V0 with respect to time is equal to 0. Similarly, we also know that VR equals IR. Hence, we can replace as well in the voltage law, such as Vi minus RIR minus V0 is equal to 0. Differentiating against both sides, we get that the derivative of the voltage I with respect to time minus R multiplied by the derivative of IR with respect to time minus the derivative of V0 with respect to time is equal to 0. Now, looking first at the current law side, we can multiply both sides by RL. On the right side, multiplying something by 0 remains 0. However, on the left side, we get that RL multiplied by the derivative of IR with respect to time minus RL multiplied by the derivative of IL with respect to time minus RLC multiplied by the second derivative of V0 with respect to time is equal to 0. However, we know that VL is equal to L, the inductance, multiplied by the derivative of IL with respect to time, which is also equal to V0, as we saw earlier according to the voltage law. So we can write that RL dir over dt, so the derivative of IR with respect to time, is equal to RV0 plus RLC multiplied by the second derivative of V0 with respect to time. So here all we did is replace L with the L multiplied by the derivative of IL with respect to time by V0 as stated by the equation. And V0 is a given value in that circuit, so it's solvable. We have it in a real life model. Now looking at the voltage law side, we have that the derivative of Vi over dt minus R multiplied by the derivative of IR with respect to time minus the derivative of V0 with respect to time is equal to 0. This is equivalent multiplying both sides by L, the inductance, to L multiplied by the derivative of IR with respect to time minus LR multiplied by the derivative of IL with respect to time minus L multiplied by the derivative of V0 with respect to time is equal to 0. Eventually, with a bit of algebra and identifying the sides that are equal to each other, we can put these two equations together to finally give the model of this parallel RLC oscillating circuit, which is that the derivative of the voltage Vi with respect to time is equal to R divided by L multiplied by V0 plus the derivative of V0 with respect to time plus RC multiplied by the second derivative of V0 with respect to time. It's important to highlight that in this equation, the only unknown is Vi, and that's what we're trying to find, right? We know what R is, it's a given when you build your circuit. We know what L is, it's also a given when you build your circuit. And we also what V0 is, because that's what we're basically aiming at where the circuit is built. So we now have an equation. Oh, sorry, we also know the capacitance, of course. So we have an equation full of known variables. All you have to do is plug in the numbers and you will find the rate of change of the voltage Vi with respect to time. So the rate of change of the voltage at the source. The last configuration I want to look at is the brushed DC motor. Essentially, what it is a stator and a rotor. Converting that to an electrical circuit, what we get is a voltage source in series with a resistance Ra and an inductor, which is the coil or the armature, La. So the motor produces a torque Tm, which is proportional to the armature current Ia. We can therefore write that Tm is equal to Ktia, where Kt is the motor torque constant. Again, it's a given depending on the manufacturing of the motor. When the motor rotates, a voltage known as a back EMF or electromotive force, EB, is generated, which opposes the applied voltage. The back EMF is proportional to the speed of the motor, and we can write that EB, the back EMF, is equal to Ke multiplied by the derivative of theta, which is the angular speed of the motor. So I mean theta is actually the angular position of the motor, and the derivative of this angular position is the angular speed of the motor. So what you can see is that, again, there's an electromotive force constant given by the manufacturing of the motor, and the fastest the motor is turning, the higher that electromotive force becomes, and therefore the lower the power output of the motor can be. Just to make it clearer, guys, the back EMF is actually a voltage created by the motor itself when it gets rotating faster and faster. That voltage is opposite to the voltage that is applied to the motor from the battery or the power source, and therefore effectively is decreasing that external voltage. So the faster the motor turns, the least effective voltage it is seeing. So it's actually what limits the velocity and the power of motors. It's that back EMF which grows as the motor turns faster and faster. In this last slide, I aggregated mathematical modeling formulas that occur very often, so are very common models or configurations in mechanics or electronics. So you can see you have an equation for a 1 degree of freedom mechanical oscillator, which we did and we studied ourselves. You then have one for a multiple degree of freedom mechanical oscillators, so the mass, the damping constant, and the spring constant actually become matrices. All this means is that you essentially have multiple equations, one for each degree of freedom generally, with different constants because you have different dampers in different directions and different springs in different directions. You can definitely look it up if you want for multiple degrees of freedom mechanical oscillators. It's really not that complicated. We then have 1 degree of freedom oscillators with support motion. It's essentially adding a damper and a spring to counteract the movement in that 1 degree of freedom. We have 1 degree of freedom rotational oscillators, so we had to look at these as well. Then in electrical circuits, we have RC circuits, LRC circuits. So these are usually filters used in electronic to filter some signals and voltages, etc. We then have the equation for a DC motor, the equation for a DC motor with damping, and the equation for a fluid storage tank. So if you happen to, find yourself having to model one of these kind of configurations, you can definitely help yourselves with these formulas that are pre-made. It'll make your work a lot faster and a lot easier. So this concludes this lecture. I hope it wasn't too complicated. I mean, I tried to make it as clear as I could. If you have any questions, please don't hesitate to ask me personally. I'll be very happy to make anything clearer for you. Thank you very much, guys.